In this lecture, today we will discuss about the phasor estimation and frequency estimation techniques. As already we have discussed one phasor estimation technique, that is the discrete Fourier transform based phasor estimation technique. And in this class, we will discuss about another technique, that is the least square error based phasor estimation technique. Now, the question comes that if we have already discussed one phasor estimation technique, then why we are interested for this particular phasor estimation technique. I will just discuss here 2-3 points that why we are interested for least square error based phasor estimation technique. That if you could see that in case of discrete Fourier transform, that we are not able to estimate the phasors of the subsynchronous frequency components of the signal. What is the meaning of subsynchronous frequency component of the signal? The signal which is having frequency below the fundamental component, that particular signal is known as subsynchronous frequency component based signal. Now, if some signals are having supersynchronous frequency component, means if the frequency is above the nominal frequency or normal frequency or rated frequency, that is 50 hertz, then that particular signal is known as subsynchronous supersynchronous based signal. Now, what happens in case of DFT, that we are able to estimate the phasor of the subsynchronous supersynchronous and the fundamental component and also the decaying DC component. But the problem here comes, the frequency which is less than this 50 hertz, that frequency is known as subsynchronous frequency. That frequency component based signal phasor estimation is difficult in case of DFT, that is the discrete Fourier transform. And also it is difficult to some extent to extract the decaying DC component part in case of DFT. So, that is why we are interested to have another phasor estimation technique, that is known as the least square error based phasor estimation technique, where we will be able to estimate the subsynchronous frequency based component, the fundamental component of the signal, the decaying DC component and also the supersynchronous frequency component of the signal. That is what we have mentioned here, that this phasor estimation based on least square error based method can be applied for signals with decaying DC component, because in power system, maybe in smart grid environment, the signal may have the decaying DC component. So, in that case we can always extract the decaying DC component using this particular phasor estimation based technique. The problem here is, see, every method has some merits and also demerits. This least error square based technique has the demerit also. What is the main demerit? The first one is it involves the matrix inversion. In the subsequent slides we will see the mathematics, the basically the formulation of this particular technique, where you will find this inversion of the matrix is involved in calculating or for calculating these phasors. And also the size of matrix increases with increase in sampling rate. That is also one disadvantage of this particular. It's not disadvantage, yes, of course, with capability of the computing facility of or the capability of the processor of the computer, we can always apply this particular technique for estimating the phasors. And also the number of variables to be estimated. So, these are 3 points which are basically the major concern as far as this least square error based phasor estimation technique is concerned. Coming to the mathematical formulation of this particular phasor estimation based technique, let us start this A plus Bt is equal to M, where this M is the measurement and T is the time and AB are the unknowns to be estimated. Now, as the quickly one question comes to my mind, that the technique is known as least square error. So, we are basically trying to calculate some error, and we are also trying to basically minimize that particular error. So, what is that error basically? The error is, this error is basically nothing, the estimated value minus the measured value. Because in power system or smart grid environment, we are estimating some parameters or some quantities or some signals, and also we have measured signals. The difference between these two should be minimum. So, whatever the signal we are measuring, so that particular signal should match to our estimated signal. So, that is what the difference, and that difference is known as error. So, in this Phasor estimation based technique, we are trying to minimize this particular error. So, in this process, by minimizing this error, we will be able to find out the unknowns or unknown variables. That is what the main goal of this particular technique. So, coming to this mathematical formulation of this particular Phasor estimation based technique, we have already defined here one equation. In this particular equation, we have this measurement on the right side, and the left side we have the estimation. And from this formulation, we will see how the unknowns are basically calculated using the least square error based technique. Let us say we have n number of measurements in our power system, and this is the first equation, this A plus BT1 is equal to M1, first equation. This is our second equation, this is A plus BT2 is equal to M2, and this T1 is at time T1 and this T2 is at time T2. The measurement which is basically done or which is in our hand, that M2 is at time T2. And similarly, coming to nth time, that is Tn time. So, the last equation, that is our nth equation, that is A plus Btn is equal to Mn. So, if you see, we have this A cap and B cap are the estimated values, because we are here to estimate our unknowns. A and B are unknowns, unknown variables. So, we are here to estimate the unknown variables from the known quantities or known signals. So, that is why this A cap and B cap stands basically the estimated values of the we are going to estimate the parameters or variables. So, this A cap and B cap are the estimated values. Now, this A cap plus B cap, this T1 minus M is equal to E1. Already we have discussed, this is basically my estimated thing and this is my measured values. So, difference between these two basically leads to the error, and that is why this is my first equation. And similarly, we have second, where we have this A cap plus B cap T2 minus M2 is equal to epsilon 2, so on, and we have nth equation. Nth equation, we have A cap plus B cap Tn minus Mn is equal to epsilon n. So, in this process, we have n number of equations, and further we will just frame one matrix equation from where we can always calculate the unknown variables. This is how the previous all the n number of equations look like. This is the first matrix, we call it as A matrix. This is A matrix, and this is our variable matrix, the unknown variable matrix A cap and B cap, and this matrix is our measured signal matrix M1, M2 up to Mn, and the last one is our error matrix E1, E2, or you can sometimes we can call it epsilon 1, epsilon 2 up to epsilon n. Now, if we just make this matrix, it will look like this A cap, this A matrix into X cap. This X cap is nothing, that is basically what the parameters we are going to estimate. This X cap stands for the unknown matrix, unknown variable matrix, and this is our measured signal matrix and epsilon. Finally, if we will see that, if we will just take the epsilon transpose and multiply on the both the sides. If we multiply, I have just taken after this equation. So, what we will do, we will take the epsilon transpose, epsilon matrix transpose, and you multiply on the both the sides, left side and the right side, and then what we will do to minimize the error, because our aim is in this process to minimize the error to get the parameters, that is what our target. So, to minimize the error, so we have to differentiate this particular equation with respect to the error and again you will equate to 0. This is a process in the matrix that if you want to minimize some parameter something, so we have to differentiate it and then we have to equate to 0. So, this equation should be taken, should be differentiated with respect to the error and it should be equated to 0 to get the unknown parameters. Finally, after doing this process, we have this unknown matrix, that is our X cap. So, this X cap stands for whole matrix into the measured signal matrix. So, this matrix is known as the pseudo inverse of A. The pseudo inverse of A is a very critical condition, that is what already from the beginning I have started that the major demerit of this particular method is to have this inverse of a particular matrix, and if the size of the samples increase then obviously it will be difficult to calculate the inverse of the matrix. So, that is what the major demerit of this particular technique. After knowing this, because you know this A matrix is already known to us and this M matrix is also known to us. So, by knowing this too, obviously we can always calculate this X cap, that is our required signal or required parameter or whatever the values we need to calculate. So, obviously we can calculate using this particular equation. And this is we in the matrix also, this in platform it is nowadays using the MATLAB, it is very easy to calculate the pseudo inverse just using one P pseudo. So, using that particular concept we can always calculate the inverse of a particular matrix. Now, we will just apply this concept to our power system signal, where we have voltage signal, we have current signal. So, how we can apply this particular phasor estimation based technique, so that we can calculate the phasor of the fundamental frequency component of the signal or the subsynchronous frequency component of the signal or the phasor of the supersynchronous component of the particular signal, or also sometimes the decaying DC component which is present in a particular signal. Now, I have just taken here one current signal. This current signal starts like IK. This K stands for at kth instant of sampling we have considered the signal IK. We can also write, if you could remember in the previous class we have discussed the sampling of a particular analog signal. We are sampling at a particular frequency 1 kilohertz or 2 kilohertz, 3 kilohertz or 1, depends our requirement. So, we have discussed 1 kilohertz sampling frequency, that Fs is equal to 1 kilohertz. In this case we have this capital N, the number of samples per cycle is equal to 20. Number of samples per cycle, we should write number of samples per cycle, that is 20, this N, that is per cycle. Now, that is what if I have some analog signal in time domain, this is basically in time domain, and this is how this small Vt stands for, or small it, whatever you can designate is possible, no problem. We can take the current signal, also we can take the voltage signal. So, here I have taken the current signal. So, let us concentrate on the current signal. This particular signal can be sampled to the discrete domain. The discrete domain means this K is equal to K into Ts. This capital Ts is nothing, the sampling time interval. So, at what interval we are just picking off one sample from the analog signal, that is what here it is 1 millisecond, because this is basically what 1 upon 1 kilohertz, that is why this is 1 millisecond. After 1 millisecond we will just catch one sample from the ADC, that is the analog to digital converter. Now, so in this manner, so we have here the discretized signal, it looks like this. So, here we will get the sample values corresponding to the analog values, and this is, and these are the discretized values. That is what this K stands for. The K stands for at, this is a sample position. Here the K is equal to 1, in this case k is equal to 2 and so on. So, in a particular cycle this k stands for k is equal to 1 to k is equal to 20 for one particular cycle. As we have discussed that if I will just maintain the sampling frequency as 1 kilohertz. So, in this case my number of samples is equal to 20 samples per cycle. That is what I just want to mention here. This Ik stands for the sample of the signal at kth instant. So, I will just write here this is equal to I1, this capital I1 into sin k omega naught Ts plus phi. The first term of this particular equation is the fundamental signal, the fundamental frequency component of the signal, and the second one, this second term is Is sin k omega naught minus omega m into Ts. This is very important term. Already we have discussed that this particular phasor estimation based technique allows us to estimate the subsynchronous frequency component of the voltage or current signal. And the last one is the decaying DC component, that one also we can estimate using this phasor estimation based technique. Now, if you see, I just want to decompose this three terms, so that we will just in the process of formulating the least error square technique, where we are interested to calculate our unknown values, unknown phasors. Already we have discussed phasor means, the phasor means we have magnitude, we have phase angle, as of course it is linked with one frequency component. The first term is basically the fundamental frequency component, where this omega naught stands for the 250, I mean it is 2 pi f naught. This f naught is basically 50 hertz component. Now, for this first term, if you will see, I have just decomposed using this formula of trigonometric equation, that is sin a plus b, that is sin a into cos b plus cos a into sin b. So, in this manner the first one is decomposed, and it is written here the known terms. The first known term to us is sin k omega naught Ts, and the second one is cos k omega naught Ts. Let me write here, if you just open it, it will be sin k omega naught Ts into cos phi plus cos k omega naught Ts into sin phi. Just I am just opening this the first term. If you write the trigonometric equation of the sine function, sin a plus b. Now, if you see this one here, the sin k omega naught Ts is known. Why? Because k is basically the sample position or sample number, omega naught is also known to us, that is 2 pi f naught, and Ts is equal to 1 millisecond. Already we have discussed here that we are taking the sampling frequency as 1 kilohertz. That is why this Ts is also known to us, that is 1 millisecond. And the second one, this cos phi is not known, the cos phi is unknown. So, we have to estimate this cos phi, that is the first variable for us. Similarly, coming to the second term, that cos k omega naught Ts is also known to us, but the sin phi is not known to us. This is the second variable. If you similarly, if you just keep on decomposing, I am opening this particular also equation, the term, and also this one. So, finally, we will have 6 variables, 6 unknowns and 6 known quantities. That is what we have designated like A11, the first one known quantity, this A12, that is the second one which is also known to us, and third one we name it A13, that is also known to us, because omega naught and omega m, the fundamental frequency and the subsynchronous frequency component is also both of them are known to us, and Ts is also known to us. And similarly, for this A14 is also known, A15, A16. Here I just want to discuss one point, that how this A15 is equal to 1 and A16 is equal to minus KTS. If you see the last term of this equation, that is k naught e to the power minus KTS by tau, that is basically the exponential term, exponentially decaying DC, because it is a decaying DC component term of the current signal. I just want to open this. Well, how does it look like? Here we will do it. This is k naught. If we write e to the power x, so how the equation look? 1 plus e to the power x, I mean that is x to the power 1 divided by x1 1 factorial plus x square divided by 2 factorial, so on. So, in this equation what is this x stands for? The x is equal to nothing, this is your minus k Ts divided by tau. You know, for this decaying DC component, k naught is the gain and this tau is equal to the decaying DC time constant, and this Ts is our sampling time period, and this small k is the kth instant or sample position number. So, in this process we have two unknowns, that is basically this k naught and the small tau, this one. So, these are the unknowns and this small k and Ts are known to us. Now, if I will just put this particular equation to this our decaying DC component based part of my current signal, now it will just behave like this. This is equal to, I will write here k naught 1 minus k Ts divided by tau, omitting the higher orders. If we just omit the higher orders, so our equation will look like this, and further if we will go k naught minus k naught small k Ts divided by tau. So, that is why this if I will take basically this k naught as one variable, here will come to this point, then in this process here this is equal to k naught into 1. So, this 1 is known to us, that is why this A15 is equal to 1. And similarly here A16 further minus k Ts whole into k naught divided by tau. So, this is basically known and this is unknown, and that is why this A16 is equal to minus KTS. That means first we have the known values and second we have the unknown values, unknown parameters or unknown quantities. In this process we have written this Ik is equal to A11 x1 plus A12 x2, A13 x3 plus A14 x4 and so on. And coming to this matrix form, A into x is equal to B. That means this x is basically the unknown variables matrix, the matrix of the unknown variables, and this B is the measured signal. Already we have discussed the mathematics of the least error square based technique, that this M basically relates to this B matrix. Already we have discussed that M is the measured signal matrix. So, similarly here the B stands for the measured signal matrix, and this A is also known to us, that already we have modeled here. The signal is already modeled like this, as if that signal, this current signal contains the fundamental, the subsynchronous frequency component and the decaying DC component. So, that is why this A matrix is also known to us. So, now by taking this X, the unknown matrix, so this is our pseudo inverse of A matrix into the measured matrix, that is the measured signal matrix, that is B. So, at every instant of time we are just taking the samples of the current signal. So, that matrix is basically the B matrix. If you see finally this A matrix is presented here. So, the dimension of this A matrix is how much? We have, as I said, we have taken here 20 samples per cycle. We are taking here one cycle data, one cycle sample of the current signal. So, in this case it will go up to 20th row. Okay. So, in this case we have 20 cross 6, 20 number of rows and 6 number of columns. So, that is why the size of this A matrix is 20 cross 6. What about this if we will come to here B matrix? This B matrix stands for all the samples we have collected with respect to time k is equal to 1 to k is equal to 20. So, we have all the samples of the current signal. We have measured at different time instant, like t stands for 1, I mean some sample 1 millisecond, 2 millisecond, 3 milliseconds up to 20 milliseconds. So, in this process this B matrix size will be how much? So, it will be, we have 20 number of rows, it will be 20 cross 1, this B matrix, and already we have discussed this A matrix size is 20 cross 6. And what about this X matrix size will be? So, this X matrix size, if you will see here, it will be 20 cross 6 into 6. We have to take the transpose, of course. This is how this matrix stands for A matrix 20 cross 6, and this B matrix, if I will keep this dot, this symbol, it stands for transpose. Transpose. This symbol stands for in the matrix formulation or matrix calculation, the MATLAB program. Now, if I will do this, so initial this B matrix, if the B matrix size was basically 20 cross 1, so it will just it will be opposite. It will have 20 number of columns and 1 row. So, it will just transpose, if we will take, it will be 1 cross 20. For multiplication purpose, we are just doing this. For multiplication purpose, we generally took this transpose for easier calculation. Now, finally, we have this X matrix. This X matrix, if you see here, we have 6 number of variables, and the size of matrix, if you will not take the transpose, it will be how much? It's just like a column matrix, where we have 6 number of rows and 1 column. Now, if we take the transpose, it will be just opposite to us and opposite to the previous number. Now, this is all about the matrix formulation of this particular least error square based technique, where we have applied the technique to estimate the fundamental components, or we are going to calculate the subsynchronous supersynchronous frequency component of the particular signal, or we are going to calculate the decaying DC component of the signal. Now, you see how we are going to calculate this x1 and x2. After multiplying this A inverse into B, so we will have this x1 value, x2 value, x3, x4, x5 and x6, so on. Now, after getting this, if I know this x1 value, let us say something about, let us say A, and this x2 is equal to B. So, what about this, the fundamental components? Now, this is the basically the fundamental frequency component phasor values we are going to calculate. If you could remember that this x1 is basically I1 cos phi 1, and this x2 is equal to I1 sin phi 1. That means, we now calculated, we have estimated the fundamental frequency real part and the imaginary part. This I1 cos phi 1 is the real part, and this x2, that is I1 sin phi, is the imaginary part. So, if you know these two components, it is very easy to calculate the magnitude part and as well as the phase angle part. If you could see this equation, this I1 is my fundamental frequency component magnitude, and this phi is the basically the fundamental frequency phase angle. That is how we will calculate. This is basically equal to I1 cos phi, and this is equal to I1 sin phi. Now, what about this magnitude? This I1 is nothing, is equal to A square plus B square root over, and this phi is nothing, tan inverse of B upon A. So, it is very easy to calculate all the frequency components, I mean using this particular technique, and similarly also we can go for this x5 x6, where the decaying DC components are present. If you could see here, this x5 is nothing k naught. If you got this x5, that means we know the basically the constant of the decaying DC, gain of the decaying DC component. And after knowing this k naught, so if you put in here, so obviously we will get the time decaying DC component time, that is the tau. So, it is very easy, already we have discussed how to calculate the frequency, the phasor estimations of different frequency components of a particular signal. This is how we have demonstrated one signal by taking 20 samples. This is how this AP looks like, and this is how this measured signal looks like. So, after that we can always calculate this x cap. This x cap is basically the estimated parameters or estimated phasors. And this is one demonstration where we have taken the current signal and the corresponding angle, this is the magnitude and this is the angle of this particular signal. Now, the second part will come here, that how to estimate the frequency, that already we have discussed in our previous lectures, that the frequency estimation is also very important in power system, or even you can say in your smart grid environment, where we have of course, every time we are going to basically have this frequency measurement or frequency estimation. If you could remember in case of our wide area measurement based technique, where the frequency estimation is one of the important technique, and for this islanding detection also we need this frequency estimation based technique. So, that is why we will discuss two techniques where we will see how the frequency can be estimated of a particular current signal or even for a voltage signal. The first technique is the zero crossing based technique. It is very easy one, but the technique is erroneous when the signal will have some basically noise. The noise will create problem. This method measures the time between two zero crossing. This is important. This particular method measures the time between two zero crossing point and calculate the frequency from the measured value. This is the basically the concept of this particular technique. First of all, we have to detect the consecutive zero crossing time, and after getting that time period we can always calculate the frequency. That this is how the equation looks like, this f of Tm, because this frequency is dependent on time factor. We have to basically measure the time of zero crossing, at what time the first zero crossing has occurred, and next what is the time where the next zero crossing has occurred. So, that is so on. So, we have to basically measure the time. That is why I have written here f of Tm, the frequency is a function of time. What is this m stands for? This m is the number of zero crossings. If you could see your previous equation, I mean the diagram signal, see here the equation is m minus 1 by 2 whole into 1 divided by Tm minus T1. In the previous equation, if you see this signal, we have started here, that means m is equal to 1, this is my first zero crossing, here m is equal to 2 and here m is equal to 3. So, we have seen 3 zero crossings. So, by putting this m is equal to 2, so I can always write 2, this is 3 minus 1 divided by 2 whole into 1 upon this Tm minus T1, starting time and the end time. That means we have started here, in this case the whole time period, say one cycle time period 20 milliseconds. The difference between these two, it should be equal to 20 milliseconds. That is why it will be 20 milliseconds. So, in this case that means we are going towards, that is our capital, I mean f, the fundamental frequency, that will be 50 hertz. So, this is how we basically calculate the frequency of a particular signal by detecting the zero crossing. Next we will go for phasor estimation based technique. I mean this is basically from the phasors we are going to calculate the frequency of a particular signal. If we know the phasors basically of the voltage or current signals, then always we can calculate the frequency. Let us say at certain time T1 we have the phase angle of a particular voltage or current, let phi 1, and at time T2 the phase angle is basically phi 2. Take the difference, because you know that our phi is equal to omega t. Omega t is how we will write, this is 2 pi f into t. If suppose we have a certain signal at certain time, at time t is equal to 1 millisecond. So, here at this point Ts is equal to 1 millisecond and ours let us k is equal to 1, the sample position. We have samples, I mean the phasors, basically the phasors, corresponding samples and corresponding angle basically we are taking here. So, at time t is equal to 1 millisecond and k is equal to 1, and next if we will go, so t is equal to 2 millisecond and k is equal to 2. If we will take the angle of this particular signal, so angle looks like this. The first angle at k is equal to 1 and this is the second angle, because we are basically calculating the phase angle and the magnitude of that particular signal using the Phasor based technique. So, from the phase angle we are going to calculate the frequency. The first phase angle is phi 1 and this is phi 2. Now, what is the difference between these two? Phi 2 minus phi 1 is equal to 18 degree if we will take the sampling frequency Fs is equal to 1 kilohertz. How does it matter? How it comes like this? Because you know the total signal angle theta is equal to 360 degree, and how many samples we have? 20 samples. So, if we divide by 20, it comes to be 18 degree between two consecutive samples. Yes, remember this sampling frequency affects the phase angle difference. Now, this 1 kilohertz leads 18 degree phase angle difference between two consecutive samples. Now, if I know this theta 2 minus theta 1 is equal to 18 degree, and what about this theta 2 minus theta 1, that is 2 pi f, what about this theta 2? The theta 2 is equal to 2 pi f k Ts, that is k 1 Ts minus 2 pi f k 2 Ts is equal to 18 degree. So, this should be 2, this should be 1. Now, if we take common 2 pi f whole into this particular k 2 minus k 1 whole into Ts is equal to 18 degree. Now, just you divide. Now, this 2 pi f is equal to 18 degree divided by this k 2 minus k 1. The consecutive signal, I mean the positions difference is always 1, that means it is equal to 18 degree divided by 1. Now, this frequency is equal to 18 divided by 2 pi. So, here we missed one term, that is the Ts. Here it is, this Ts will come here into Ts, 1 into Ts. Now, it leads to 50 hertz. So, this is a very important concept where the frequency of the particular signal can be calculated using the Phasor based technique. If you know the phase angle of a particular signal, so consecutive phase angle we have to just track, and by taking the difference between these two, divide by this 2 pi and Ts. So, we can always estimate the frequency of the signal. So, in this particular lecture we have discussed very clearly the difference between this DFT and the least error square based Phasor estimation based technique, that why we are interested for this Phasor estimation technique based on the least error square, because here we have the major advantage, like we can extract the phase angle or magnitude of the subsynchronous and supersynchronous frequency components of the signal, and also we can calculate the decaying DC component of the signal, the gain and the time constant. And also we have discussed very clearly the frequency estimation of the signal using two techniques, that is the zero crossing based technique and also Phasor based technique. Thank you so much.